Get started. Um, all right, what is backpropagation? I guess that's the first thing we need to consider, and it's really a method used in artificial neural networks to calculate a gradient. That is a change that's needed in the adjustment of the weights to be used in the network, and the term backpropagation really is shorthand for the backward propagation of errors. That is because in a neural network, information is fed forward, and errors are fed backward, and through the network's layers. And in general, what we'll find is that the current method, what we call backpropagation, is really a generalization of what's called the single layer delta rule, and that single layer delta rule, well, as its name says, was applied to a single layer of neurons. As you'll see when we get to to networks that have more than that have a hidden layer between the input and the output, we need the chain rule to compute the gradients. And I'll talk about a gradient in a second, I think in the next slide, as to how we decide how to backpropagate the error. But basically, in the context of neural network learning, backpropagation is used by an algorithm that we call gradient descent to adjust the weights of the neurons. And really, that gradient descent algorithm, again, that we're going to consider in some detail, is really the gradient descent algorithm is designed to decrease the error along the lines of the sharpest decrease in the error function of the network. And again, we'll talk about what that error function is, or loss function, you could also call it, for the network. So, I mean, why are we doing this? Why do we backpropagate the error? Right? We want to train the neural network to provide the best approximation to the signal that we're trying to have it learn. And again, on the right here, there's no big particular significance to this slide, except for a general picture of what backpropagation is, and so no need to really study it in too much detail. At least for now. So a couple of terms that you're going to hear tossed around, and they're not exactly interchangeable, but they're all related to backpropagation. And those terms are gradient descent, delta rule, and backpropagation itself. Now, gradient descent, and again, I sort of alluded to this earlier in the last slide, it's a way to find the minimum value in a high-dimensional space, meaning in the gradient descent method, you actually go in the direction of the steepest descent. In this particular error situation, it's error. Now, I've shown a one-dimensional, if you will, error surface on the right slide, on the slide on the right, and basically, gradient descent is moving is in effect changing the weights such that this ball, which is, I guess, our position in the error function, which is this parabola, also called a cost function, and whatever, right? We want to move the ball down to the minimum weight, which is at the bottom of the parabola. And the gradient descent method, if this were the error surface, would take us in that direction, meaning it wouldn't take us up, because it would take us in the direction of decreasing error. And in particular, when you've got a more complicated error surface that's the product of many variables, as we'll see later on, it's going to do this in a multivariate case. And how it does it is by using the partial derivative of the loss or error function to propagate the updates to the neural weights. Now, the delta rule, okay, which it is in a sense a variant of the gradient descent rule, where you have only only one weight you can think of, and it again, and what we're looking at here on the right in the figure is really more of a generalization from the delta rule, because the delta rule can be applied directly because it only has one weight, whereas you'll see when we get to backpropagation that you're going to have to use the chain rule, because we have input level neurons feeding second level neurons feeding the outputs, and it's really the fact that we have this other layer in here that requires us to take into account not only how a change in the input variable and its weight affects the output, but changes in the weights that the neuron that the input variable feeds also change. And so anyway, and that's where backpropagation differs from the simple delta rule, which I think I'm going to show you in the next slide. But in any case, backpropagation is an efficient implementation of gradient descent. Yeah, so let's move right along. Yeah, so here is the delta rule, okay? And the delta rule is fairly simple, okay? Basically, the thing to remember is that it's only the delta rule itself can only be applied to neurons in a single layer neural network. That's why it's a special case of more general backpropagation. So for a neuron J, right, with an activation function G of X, the rule for J's ith weight, or the change the weight, is given by this equation where delta WJI, which is the change in weight, is equal to some alpha, which is our learning rate, okay? And I'll say we're going to say a lot about that. And basically T of J is just what's the target weight of the neural network, right? In response to this, well, Y is actually the actual output. So we're looking at the difference between the target output and the actual output times the derivative of the activation function, which is that's the G prime, HJ. HJ is the output of the neuron, and G of HJ is the derivative of that, and times actually the input that we're in question, right? The XI, and that's it. And so sometimes people just state it very simply at the bottom here. And again, I just showed you that HJ is equal to the sum of the XI's times the WJI's, and so forth, and YJ is just the HJ put through the activation function. Anyway, so, and you can simplify it to not worry about the activation function at all, and just as a change in weight for neuron J for input for the ith weight is simply the learning parameter times the error times X.